Alrighty, howdy folks. Let's look at 2.5, section 2.5, and this is the last section in chapter 2. With this, after this we'll move on to higher order differential equations. So let's get started. So this one is about solving first order linear equations. What all did we do so far? 2.2 was about separation of variables, then first order homogeneous equations, then first order exact equations, and these are linear equations. So that's what we're going to learn. Cool? For this, I'll ask you to recall the form of an nth order linear ODE. Right? I must have tortured you with problems from 1.1 where you had to recognize, hey, is this given equation linear or not, right? And what order is it and stuff like that. And there you saw this stuff. What is it? Every derivative term must be raised to a power of 1 if it appears, right? Including the 0th derivative y. And every coefficient must be a function of x alone. And if there are any terms with a y in it, they should be on the left-hand side. And the terms that do not have a y in it should be on the right-hand side. Like the x terms, pure x terms must be on the right-hand side. So that was the nth order linear equation. Now if I were to ask you, hey, can you tell me what a first order linear equation would look like? Would you be able to do that? This is for nth order. What would the first order be? Oh, that means d to the ny would be d to the 1y, or simply dy dx, and the coefficient would be a1 of x. So we have the first term of the differential equation on the left hand side would be a1 of x dy dx. Hey, this is the term, a1 of x dy dx. After that, we should have a plus a0 of xy equals 0 g of x. So that's what I'm saying here. Cool. Now, how do we solve equations of this kind? What I'm planning to do here is I'll illustrate the whole procedure with an example. Okay. Say this one. First things first. Does this look like a first order linear equation? Some a1 of x dy dx plus a0 of x times y equals some g of x? Yep, it does. So how do you solve this? The first step is, there are a few steps, I think about 4 or 5 steps. The first order of business is, when you see your differential equation in this form, divide throughout by the coefficient of dy dx, that is a1 of x. When you do, would you agree, you get dy dx plus a0 of x over a1 of x times y, and g of x on the right hand side, g of x over a1 of x. And so what I'm saying is, take that a0 of x over a1 of x and call that as a p of x. Similarly, the g of x over a1 of x, call that as f of x. As simple as that. So make sure that is the first thing that you do. Basically, you want to make the coefficient of dy dx to be 1. Cool? Alright. And so, for this problem, if we were to apply that, we need to divide throughout by x. So it becomes dy dx minus 4 over x times y equals x to the 4 e to the x, right? I divided x to the 5 e to the x by an x, so it became x to the 4 e to the x. Step 1. Step 2, identify what p of x and f of x are. Right? Can you do that? In the sense, this guy, dy dx minus 4, is in the form of this. So just compare and say, so that means p of x must be negative 4 over x. Yep. And f of x must be x to the 4 e to the x. Cool? So that's the idea. So identify p of x and f of x in step 2. Now it's possible that sometimes I might combine steps 1 and 2. Write it and immediately say, okay, based on this, p of x is this and f of x is this. Okay? All right. And then we need to evaluate integral p of x dx. Now I agree. I'm not telling you, why do you do this, man? I simply seem to be saying, trust me, this is the procedure. But then there is actually a logic behind all of this. Hopefully when we get to the final step, I'll explain that logic, why I'm doing what I'm doing. Okay. Evaluate integral p of x dx. What is p of x? Oh, negative 4 over x. Cool. So that's integral negative 4 over x dx. And when you evaluate that, you get negative 4 natural log of x, which we know based on properties of logarithms that coefficient becomes the exponent. So we can write that as natural log of x raised to negative 4. You agree with that? Cool. And in the next step, we need to find something called the integrating factor called mu of x. We need to find mu of x, the integrating factor. How do you do that? E raised to integral of p of x dx. In the previous step, we did find integral of p of x dx, so it must be fairly straightforward business of just plugging what the integral of p of x dx is. So e raised to that integral, so that means e raised to, in our case, natural log of x to the negative 4. But then wait a minute, isn't there a property like this? E to the natural log of m is just m. So this must equal x to the negative 4. Are you cool? So we found that integrating factor mu of x by doing e raised to integral of p of x dx turns out to be x to the negative 4. Cool. What's the next step? In the next step, we need to find integral f mu dx. What do I mean by that? F is our f of x. Do we have f of x? Yeah, from step 2 we have f of x, that f. And mu we found in step 4. Mu is x to the negative 4. So find integral f mu dx in this step. So we end up getting x to the 4 times e to the x is our f of x. Mu happens to be x to the negative 4 dx. Right? And would you agree that the integral of this is just e to the x? What? How'd you get that, man? Well, x to the 4 times x to the negative 4 is just 1. So 1 times e to the x. And that's e to the x. Right? Integral e to the x dx is e to the x. I lied. I said there are 5 steps. There are 6 steps. And the solution is y mu equals integral f mu dx plus c. Cool, folks? The solution is y mu equals integral f mu dx plus c. Okay, when we say find the solution, we want to find y. But in this case, it just so happens, excuse me, I'm going to cough. In this case, we have y times mu. The way the solution comes out is we will have a y times mu on the left hand side. That's an easy form to remember instead of saying divide by and all. This is an easy form to remember. That's why I'm putting it in this way. So y mu, y times mu, must be equal to integral f mu dx plus c. And here all I'm doing is plugging in mu. Step 4, set x to the negative 4, y times x to the negative 4. Integral f mu dx is e to the x from step 5. That's what I plugged in. Plus c. I said plus c. And let me tell you, it's absolutely vital that you put a plus c here. I will take off a big chunk of points if you do not put a plus c in this case. It is that important. I'll tell you why. That is because if you do not have a c, then you will be missing out a big chunk. What do I mean? Let us say you do put a C. Contrast that not putting with a where you do put plus C. Now, would you agree y itself is e to the x times x to the 4 plus c times x to the 4. What did I do? I multiplied both sides by x to the positive 4. So y equals x to the 4 e to the x plus cx to the 4. If you do not put that plus c here, you will completely miss out that term cx to the 4. Missing a plus c itself is a blunder, but missing a plus cx to the 4 would be an egregious blunder, right? That is why you must put a plus c in this solution process at the end. All right. So I'll solve quite a few examples so that this concept is clear. But as you can see, it's just a stupid process. Step 1, 2, 3, 4, 5, and you're done. In a way, that's what makes differential equations not so difficult. Especially if your integration skills are good, differential equations is a piece of cake. Okay? And so what I've done, I owe you an explanation as to why we followed the steps, but I'm going to do that in the next slide when I just summarize the whole thing. I just want to give you just the steps alone. Step 1, you do this and divide both sides by a1 of x, and then identify p of x and f of x. Evaluate integral p of x. Right? These are the steps. Now let's ask, why do we do this? Why do we go through these steps? It is because if you look at the very last thing, this is our, what's that American expression? The money statement or the money result. All this was we were working hard and finally we get paid at the end, right? So when you look at this, y is what we need to find our solution. Y equals some function of x is the solution of our differential equation. So that's the y. So it has a mu in it. So the question then becomes, hey, what in the world is that mu, man? Oh, mu happens to be e raised to integral of p of x dx. Oh, okay. So what is p of x? Oh, p of x, that's why we divided by a1 of x here throughout, and we got the coefficient of y put to be p of x. Oh, so that p of x. So, to get mu, you need to know p of x and also the integral of p of x dx. And in addition, once you get that, you need to figure out e raised to integral of p of x dx to find mu. Right? And that's why, if you notice, I'm proceeding in a logical fashion. I'm identifying p of x first, because I need e raised to integral of p of x dx. And again, in the next step, I'm figuring out the integral itself. And in the third step, e raised to integral of p of x. Right? If you were to come up with a logical process, I have a feeling you will come up with exact same one, because you have a logical mind as well. And in addition, in the right hand side, we have integral f mu dx. So the question then becomes, hey, what in the world is f? Oh, that f is this guy, f of x, which is g of x over a1 of x. Right? That's why we needed to identify what p of x and f of x are. And mu, oh, we figured this out already for the sake of the left hand side. And then it's a matter of integrating. So why not go ahead and integrate as a separate thing, just so that we can proceed in a systematic way and in chunks, useful logical chunks. That's the idea. Cool. So while I say, yeah, just kind of memorize the steps, There is a method to this madness. Okay, cool. This guy. Let's see. So how do we do this? 1 plus x square dy dx, and I divided both sides throughout by dx, and then I kept this xy on the left hand side and subtracted an x cube and x from both sides, so that we have this form. Cool. Does this look like a1 of x dy dx plus a0 of xy equals some g of x? Yes, it does. So what's our step 1? Divide throughout by a1 of x. Especially if a1 of x is not equal to 1, yep, go ahead and do that. And that's exactly what I did. And quite nicely, the right hand side simplified to negative x times 1 plus x squared over 1 plus x squared just became negative x. Cool. And so now identify p of x and f of x. What is p of x, folks? The coefficient of y, x over 1 plus x squared. What is f of x? Negative x. Right? Okay. And what's the step after that? We need to find integral of p of x dx. So get busy. Start integrating x over 1 plus x squared dx. If I said that's equal to 1/2 natural log of 1 plus x squared, would you agree with that? What? How'd you get that, man? Substitution. U equals 1 plus x squared. Du is 2x dx. And like that. And then this becomes 1/2 du over u, which is 1/2 natural log of u. Strictly speaking, absolute value, but I'm removing the absolute value because 1 plus x squared is guaranteed to be positive. So we can just say natural log of 1 plus x squared. No need for absolute. Cool. Now, if I said this is equal to natural log of square root of 1 plus x squared, would you agree with that? Oh, how'd you get that, man? Well, this 1/2 becomes an exponent of 1 plus x squared. So we have 1 plus x squared raised to 1/2, which is nothing but the square root of 1 plus x squared. Right? Cool. Any idea what the next step is? Finding mu. Mu is e raised to integral of p of x dx. So we'll raise this guy to a power of e. And what is that equal to? Again, based on the properties, this must be equal to just square root of 1 plus x squared itself. Cool? Alright, next. We need to find what? Integral f mu dx. Oh, let me say something here. Every time, be absolutely sure to say this. I'm finding integral f mu dx. Do not just start plugging in and say, okay, I got negative x times. What in the world does this integral negative x times square root of 1 plus x squared dx indicate? What does it stand for? If you don't say that, you will confuse yourself and you will definitely confuse me. And I'll be looking at it and going, what the hell is this? But if you say prior to that, hey, integral f mu dx equals this, oh, I see. This guy is calculating integral f mu dx here. Becomes clear to me and clear to you, especially when you look at your own notes. Right? Cool. So the question is, how do you solve this one? Again, substitution. I'm a nice guy. I actually showed you the substitution here. So u equals square root of 1 plus x squared. My strategy is to square both sides. I like that one for some reason, so that I don't have to deal with, if you say du, what is du now? Du is going to be 1 over 2 times square root of 1 plus x squared times 2x, and it's a pain. You will continue to have those square roots and all that. I don't have anything against square roots, but I think this is a much better way. Square both sides. And the only thing you need to be careful is the left-hand side is not just du. Because we don't have a simple u, we have a u square. That means in the next step we should say 2u du equals. Did you get it? Please pay attention to that. Because we have a u square, in the next step we do not say du, instead we say 2u du. Where did you get that 2u from, man? Well, that's the derivative of u square with respect to u. Cool? Okay, what if this were to be u cube? Well, the derivative of u cube is 3u square. So this would become 3u square du in the next step. Cool? That's the idea. So 2u du equals 2x dx, and x dx is just u du, and that's what I did. I pulled the negative sign out, and for x dx I plugged in a u du, and for square root of 1 plus x square I plugged in a u. So u times u du, and that's u square, and integral of u square is u cube over 3 with this negative outside, and tada! This is integral f mu dx. Finally, the money statement. Y mu equals integral f mu dx plus c. Cool. And don't forget that plus c. And y times, just a matter of plug and chug. You just plug, you got it. Right? That's a very nice problem. You leave it like this, I'll give you full credit. Quite possibly, if you look at the book, textbook, they may have divided both sides by square root of 1 plus x square. And that would have made the first term especially look a little more elegant, in the sense negative 1/3. Square root of 1 plus x square, the quantity is that quantity square root of 1 plus x square squared, and that would have gotten rid of the square root altogether, and would have been negative 1/3 times just simply 1 plus x square. However, this wouldn't be a plus c. See, that's the key. This would be a c over square root of 1 plus x square. Right? I don't know how much more elegance that adds. That's why I would just leave it like this. And if you left it like this, full credit. Okay, folks? Whew. Cool. A few more. Problem 18. Do we need to divide both sides throughout by a1 of x? Nah, it's already a1 of x is just 1, so it's already in the form of dy dx plus p of x times y equals f of x. So we'll just identify that p of x is cotangent x and f of x is the right hand side 2 cosine x. Next step, all of you. Integral p of x dx is integral cotangent x dx. What is that? A natural log of sine x. And the idea is we need to pick an interval where these things are continuous. Okay. And there are no discontinuities causing differentiability problems. So I just happen to pick an interval 0 to pi half. And also on the interval 0 to pi half, sine x is clearly positive. And so we don't need the absolute value around sine x. Strictly speaking, we should say natural log of absolute value of sine x. But in lieu of the fact that in view of the fact, did I say lieu? No, in view of the fact that sine x is positive on 0 to pi half, we can remove the absolute value sign. Okay, then mu of x is e raised to integral of p of x dx, and so that's e raised to natural log of sine x, which is sine x. right? Isn't that the next step after integral mu p of x dx? Cool. Remember what the next step is? Integral f mu dx. Figure that out. And that turns out to be this. And we can say this is equal to sine square x. How? U equals sine x, du equals cosine x dx. And so this simply becomes integral 2u du, which is u square, which is sine square x. Okay? And y mu equals f mu dx plus c gives us this. Cool. Next. Okay. Divide throughout by a1 of x, which is x plus 1. And p of x is the coefficient of y, and f of x is the right hand side stuff. Next step, folks, integral of p of x. How do you integrate this? I don't know, man. Well, you remember, I don't know, whenever it was, maybe in separation of variables, I talked about how I do this one. I write the x plus 2 as x plus 1 plus 1. Why x plus 1? Because the denominator has an x plus 1. If I had the top the same as x plus 2, but in the denominator, if I had x minus 3, let us say, I would have written the top as x minus 3, and then, what should I add to it so that it becomes x plus 2? Oh, plus 5. X minus 3 plus 5 is how I would have written over x minus 3. Anyway, that's what I did, and x plus 1 over x plus 1 is just 1. Integral of 1 is x. Integral of 1 over x plus 1 is natural log of x plus 1, provided we pick the interval for x to be greater than negative 1. Okay, and then mu of x turns out to be, maybe I should point this out, e raised to x plus natural log of x plus 1. Watch this one. Check this out. Right? E raised to x plus natural log of x plus 1. Now, is this in the form of a raised to m plus n, which is a to the m times a to the n? Yup. So we should say e to the x times e to the natural log of x plus 1. Okay. And e to the natural log of x plus 1 is just x plus 1. So we have e to the x times x plus 1. I wrote x plus 1 times e to the x here. Cool. So we got mu of x, and now we need to figure out integral f mu dx, and that turns out to be fairly simple. A whole bunch of terms cancelled. X plus 1 gone. E to the x times e to the negative x is 1. So we're just left with integral 2x dx, which is x squared. And finally, y mu equals integral f mu dx plus c. Plug and chug. Done. Cool? Okay. I like this. Right? Divided throughout by that, identified p of x and f of x. Integral of p of x. I think that's why I picked this one. So the question is, how do you integrate this guy? You integrate this by doing partial fraction decomposition. So to do that, first break this x squared minus 1. Break in the sense, factor this x squared minus 1 as x plus 1 times x minus 1. And then that splits into 1 over x minus 1 minus 1 over x plus 1. Okay. If you have any trouble with how did you do this, please watch a video that I posted on partial fraction decomposition in the background part. Okay. So it becomes this. And integrating this, would you get natural log of x minus 1 minus natural log of x plus 1. However, natural log of A minus natural log of B can be written as natural log of A over B. Right? Fascinating. So natural log, the integral of P of x turns out to be natural log of the quantity x minus 1 over x plus 1. In the next step, let's figure out mu as e raised to integral of P of x dx. And we get x minus 1 over x plus 1. What's the next step? Y mu, integral f mu dx. That quite nicely. Whoa. Oh, really? Now, isn't that cool? This x plus 1, there is another x plus 1 here. Becomes x plus 1 the quantity square. And there's an x plus 1 the quantity square on the top. So that's 1. X minus 1 over x minus 1, that's 1. So this whole thing just reduces to 1 dx. Huh. No wonder I like this problem. And so that's just equal to x. Finally, y mu equals integral f mu dx plus c. Ta-da! Cool? Alright. Next thing. D. Oh. It's another nice problem. Oh man, that don't look anything like a linear equation, man. Yeah, man, I agree. If we say dy dx equals 1 over 3 to the y. Oh. No. That's not linear. Not linear. Should we stop there? Not linear and... Nope, you told me to solve this linear equation, but it ain't linear, so I'm not going to solve it, man. Wait a minute. It's not linear in y, for sure. However, if we write this as dx dy, then we end up getting dx dy plus 2x equals 3e to the y. Ooh. Is that linear? You bet. Right? If you don't believe me, just in your own head, try to flip this and make it dy dx, switch x's and y's, dy dx plus 2y equals 3e to the x. Perfectly linear. Right? Except that instead of y being the dependent variable, x is the independent variable, so this is linear in x. So sometimes you may have to do this kind of a manipulation first. Okay, then the rest of it is straightforward, except you shouldn't call this as p of x though. You should call it p of y. Right? P of y equals to f of y is 3e to the y. And in the next step, where we do integral p of x dx, we actually now need to do p of y dy. And that's 2y. And the next step where we say mu is e raised to integral of p of x dx, now we need to say e raised to integral of p of y dy. And that gives us e to the 2y. And in the next step, integral f mu dx, we need to do integral f mu dy. And that's what I did. The integral of e to the 3y is e to the 3y over 3, and that over 3 multiplied by 3 just becomes 1, so that's why we have e to the 3y. Okay. Next step, final step, the money step. What is it that we typically used to say? Y mu equals integral f mu dx plus c. So in this case, what would that step, what should that step say? We don't say y mu, instead we say x mu. Instead of f mu dx, we'll say integral f mu dy plus c. Plus c is plus c. That's the idea. As long as you can make that small change, this problem is piece of cake. All right. Next. I usually try to switch everything to x's and y's, but once in a while I leave things the way they are. For example, this one, L di dt plus Ri equals E, I of 0 equals I sub 0. I leave it like this because there is some practical significance to this one. This we can write like this. I didn't even do that, huh? What an idiot I am. Sorry about this. What's the big deal about this? It is interesting because for double E guys, this represents an LR circuit. This is a resistor and this is an inductance, and there's a E, a battery here supplying EMF, electromotive force. This is L, inductance coil, and this is the resistance R. These things should be much sharper. I cannot draw sharp things, so please bear with me. So that is a resistor, and I don't know, these spikes just come whenever I write with this pen. I have no idea why that is, so ignore those spikes. Okay, so how does current flow in a circuit like this is the question about. And it so happens that the initial current at t equal to 0, there is a current of I sub 0 flowing through this. Did I show this arrow pointing this way? I think there's something about that current should be flowing this way if I'm not mistaken. Hey, I ain't no electrical engineer, man. I'm a mechanical guy. I think that's because this is negative and that is positive terminal. Why is a certain terminal negative? Because it's got more electrons in it. So when you close the circuit, the natural tendency is just like water goes from a higher level to flows from a higher level to a lower level until both the levels become equal. Electrons flow from this negative terminal. There are excess of electrons. So those excess electrons start to flow and flow through the circuit and then try to reach this one. So the amount that these electrons deplete, and then when they add, this thing keeps on going until both of them have the same number of electrons. Both the terminals have the same number of electrons. That's when a steady state is reached. Okay. Anyway, so how does the current flow as a function of time in a circuit like this? That's what this problem studies. Cool. All right. Let me erase that. As usual, divide throughout by A1 of t here, and identify P of t and F of t. Integral of P of t dt, mu of t, integral f mu dt. Turns out to be this with a plus c. Where did I do a plus c here, man? I'm an idiot. To stay consistent, I shouldn't have this plus c here, right? Okay. The only thing is, don't do a plus c here and another plus c so that it becomes plus 2c and all that. Crud. Ignore that guy. Okay. So integral I mu equals, instead of y mu, we say I mu, because I is the dependent variable, t is the independent variable. Cool? And gives us this. But then we have I of 0 equals I sub 0. That's an initial condition. We need to apply that initial condition. What did I do here? I divided both sides by e to the RT over L, and so the left side became I, and the right hand side became e over R plus e to the negative RT over L. And so applying the initial condition I of 0 equals I sub 0, that is, plug t equal to 0 and I equals I sub 0. Do that to this equation. And you get I sub 0 equals e over R plus c. What? How'd you get that, man? Well, t is 0. Makes it R times 0 is 0. 0 over L is 0. So e to the 0, e to the negative 0 or e to the 0 is just 1. So this whole thing just becomes plus c. The second term becomes plus c. That's what I have here. And so from that you can solve for c and you get I sub 0 minus e over R. Now go back and plug this value of the exact value of c into this equation again. So we get I equals all of this stuff. Right? Is that what Americans call clear as mud? There is a good amount of significance to this one. Or it looks like, if you draw a curve of this one, it looks like this. All right. Okay, what does this do, man? Let's look at the graph a little. On the x-axis we have time, and on the y-axis or on the ordinate we have I, the current flowing in this circuit. At t equal to 0, there is an initial amount of current flowing through the circuit equal to I sub 0, whatever that is, some constant, okay? 1 ampere, I don't know. So some current is flowing, that is I sub 0. And then once you flip the switch on, the amount of current starts to increase, and flowing in the circuit starts to increase, and then it levels off and reaches a steady state. That's the nature of a circuit like this. And what is the steady state value of this one? E over R. E is the voltage of that battery that you have divided by the resistance, whatever that is. So this when the current reaches a steady state, its value, the amount of current that flowing through this one is E over R. Cool? And let's see, okay, what does that mean in turn? If R is a smaller value, keep the E the same. If R is small, what does that mean? R is small means resistance in the circuit is low. When you talk in terms of bulbs, which bulb has lower resistance? A 20 watt bulb or a 500 watt bulb? A 500 watt bulb, which glows much brighter, it has a much lower resistance. So that's why a whole lot of current flows through that and causing it to be bright. The power would be I square times R. I would be so large, you are squaring it, so I square would be very high, I square times R. Even though R is low, I square actually is high. So that a 500 watt bulb would be burning brighter because of that. And in this one says, in such a case, you have a low resistance bulb, which is brighter, E over R would be a much larger number, right? R is small, so E over R dividing by a smaller number means quotient is big. So more current would be flowing through a circuit like that, or the steady state value of the current that's flowing through a circuit like that would be much higher. Okay, and so very interesting analysis can be done, and this is what you guys will do in electrical engineering. Maybe some of you were taking circuits. I don't know. Will you ever bump into LR circuits? You may. Cool, folks? I think I'm done. Yep, I am. Alrighty.